All right, let's do some problems. We're going to start with number 16 from the textbook, which says something. Find the domain, vertical asymptotes, and horizontal asymptotes. All right, and it's x squared minus 1 divided by the denominator, x cubed plus 9x squared plus 14x. The function is f of x. So remember, the domain is going to tell us all of the discontinuities, either removable discontinuities if it shares a factor with the bottom and the top, or a vertical asymptote. So let's find that domain first. Domain is all the points except when the denominator equals 0. We have to find when this is true to find that domain. So we're going to factor it. Anytime you can take out a common factor, GCF, greatest common factor, it's going to make your life a lot easier. We can factor out an x here. Everything here has an x. What's left over if you take an x out of x cubed? X squared. 9x is left from the next term, and 14 is left from the next term. And now it becomes a little easier to factor. This inside is a trinomial with leading coefficient 1. Because it's a trinomial, we know it's going to factor like this if it factors. And since the leading coefficient is 1, the only way to get x squared is x and x like this. Need two numbers that multiply to 14 that add to 9. Should be 2 and 7. Do a quick check to make sure that we did it right. X squared plus 7x plus 2x. 7x plus 2x is 9x. Good. Plus 14. Great. We factored correctly. So it's going to be every single x except when x is 0, when x is negative 2, and when x is negative 7. Solve when this is equal to 0, solve when this is equal to 0, and solve when that is equal to 0. And that gives us our domain. Our domain is everything except those points. You could use interval notation, but it really becomes very tedious when there are 3 points right here. It's going to be the set of all x such that x is not equal to negative 7, negative 2, or 0. And so every single one of these is either a vertical asymptote or a removable discontinuity. And it just depends on whether that factor is shared in the top. The top is the difference, can factor with the difference of squares. The top only has factors of x minus 1 and x plus 1. They don't share any factors. These don't have any of the same factors. So these are all vertical asymptotes. There are no removable discontinuities here. Vertical asymptote at negative 7, at negative 2. Let's list them all out. And at x equals 0. That's why they're not part of the domain, because there is that vertical asymptote right there. Last things that left is the horizontal asymptote. We can find the horizontal asymptote by looking at end behavior. So the end behavior of this is the same as the end behavior of the leading terms. Well, that's the end behavior of 1 over x. End behavior of 1 over x, we know what that looks like. Horizontal asymptote at 0. That's how you find the domain, the vertical asymptotes, removable discontinuities if there were some, and the other asymptote, I don't remember what word I said, but horizontal and vertical. Okay, let's do another one. 22. Find the x and y intercepts. F is x squared plus 8x plus 7. And x squared plus 11x plus 30. So for the Intercepts, you actually only have to look at the top. But you do have to make sure that they're in the denominator, or they are in the domain. Okay. So the x-intercept is in y equals 0. That's the solution to this equation. We solve this equation by multiplying by the LCD on both sides. The left multiplies out to 0, and the right cancels. So this is just when the numerator equals 0. That factors to x plus 7 and x plus 1. So our candidates are at -7 and -1, but we have to make sure that these are in the domain. Okay. There's two ways to make sure that they're in the domain. We can either find the domain, or we could plug these into the function and see if it causes us to divide by 0. So it's x squared plus 11x plus 30. We can factor that pretty quickly. It's just going to be x plus 6, x plus 5. So the only things not in the domain are -6 and -5. So we don't have to throw any of these out. They are in the domain. And the y-intercept is just when x equals 0. That's going to be 0 plus 0 plus 7 divided by 0 plus 0 plus 30. Oh, that was quick. Y equals 7/30. It's best to express these as points, right? -7, 0, -1, 0, 0 and 7/30. This is best. But this is okay. All right, let's do another one, 28. Describe the local and end behavior of the function. Our function here is x squared minus 4x plus 3 divided by x squared minus 4x minus 5. So local behavior, we're going to be carrying about asymptotes and arrow notation. End behavior, we're going to look at the end behavior of the leading terms. All right, so in order to know the asymptotes, we're going to have to factor. And again, if we care about local, we're going to have to factor the top two because we want to know whether they're removable discontinuities or vertical asymptotes. So the numerator, wait, did I copy that down right? No, it should be plus 3. It didn't factor before, now it does. The numerator is x minus 3, x minus 1. And the denominator is x minus 5, x plus 1. Again, multiply to 3 on the top, add a -4. Multiply to -5 on the bottom, add to -4. Okay, so there are no removable discontinuities. Removable discontinuities are just when there's a shared factor in the top and the bottom. So we know there's a vertical asymptote at x equals, look at the denominator, -5, and at x equals -1. How can we talk about that with arrow notation? Well, it's going to depend on, I think in these ones I specify that you can just graph these with Desmos. I did. I said you can just use Desmos for these. You can also solve them by hand. We look at this on Desmos. It's going to be x squared minus 4x plus 3 divided by x squared minus 4x minus 5. I think that's what we said. Great. And then let's get back to normal scale here. All right, so yeah, you can see those vertical asymptotes at -1 and 5. And we're going to explain those with arrow notation or limit notation. So as x goes to as x goes to -1 from the left, how does the function behave? From the left of this asymptote, the function's going off to, from the left to the right, function's going off to positive infinity. As the function goes to -1 from the right, as we're approaching the same asymptote from the right to the left, it's going down to negative infinity. And do the same thing for the other asymptote. As x goes to 5 from the left, going down to negative infinity, and from the right, it'll be positive infinity. This is what it looks like. You can also write these in limit notation. One such example would be the limit as x goes to -1 from the left of the function equals positive infinity. You could do these for every single one. So that's the local behavior. End behavior, we have a horizontal asymptote at 1. So you can see it on the graph that it gets really close to 1, or you can look at those coefficients, those leading terms. Horizontal asymptote at y equals 1, or again, in arrow notation, as x goes to positive or negative infinity, as x goes to the right or the left, the function approaches +1. It's a lot of writing. It's a little less writing if you use limit notation, but that's what it is. All right, 32. Find the slant asymptote. 81x² minus 18 over 3x minus 2. And again, if we just look at the leading terms, that's going to tell us the slope of our slant asymptote and that we have one. But to find the y-intercept of our slant asymptote, we're going to have to divide these out with long division. So 81x² minus 18. We're dividing, 3x minus 2. Be very careful when you're doing long division. It's a good idea to include all the terms. So like write that there's no linear term in the numerator. It's very helpful. You don't have to do this. You don't have to do this right here, but it generally makes it a little easier. I didn't give myself a lot of room on the top. All right, so first things first. What do we need to multiply to get 81x²? 27 and x. We have 27x up here. And then we multiply it and see what we get. We multiply that out. We're going to get 81x², which is good. That's exactly what we wanted. And then we're going to get minus a 54x. And that's why it's so nice to have that 0 there so everything lines up. We're subtracting this. So these cancel out, which is good. And we're going to get 54x. Drop down the next term. And again, what do we need to multiply these two things in order to get 54x? Sorry, we need to multiply these two things to get 54x. It's just going to be whatever 54 divided by 3 is, which is 18. And then we multiply 18 by each of these. And we're going to get 54x minus 36. Subtract these out. The minus 36 becomes a plus 36. And we get a remainder of 18. So this function is equal to 27x plus 18. And then our remainder is also 18. Which means that in the middle, it kind of behaves like 1 over x. Locally, it kind of behaves like this. But the end behavior is like this. So we're saying our slant asymptote is y equals 27x plus 18. Let's check our answer, especially on something like this. Our function is 81x² minus 18. We're dividing by 3x minus 2. And we claim that our slant asymptote is y equals 27x plus 18. All right, so again, we're going to have to change our scale a little bit. Let's zoom in on the x region and then zoom up a little bit on the y's. Oh, that looks nice. You can see that they're approaching that line. And in the middle, it's kind of behaving like 1 over x, but at the ends, it's approaching those lines. $46. All right, sketch a graph using the 3 things that we talked about before. X squared minus x minus 6 over x squared minus 4. Sketch a graph. So we're going to start by looking at the zeros, x-intercepts. That's going to be when y equals 0. You could do this a long way, but remember it's going to turn out to just be when the numerator equals 0. All right, and that numerator factors, here, let's just rewrite this whole thing. It's going to be very useful. The numerator factors into x minus 3, x plus 2. And the denominator is x minus 2, x plus 2. Oh, we're going to have a removable discontinuity this time. So this function is only equal to 0 when x is equal to positive 3. X equals negative 2 is not in the domain. What's the multiplicity here? Multiplicity here is 1. X equals 3. It's going to be a 0. X equals negative 2 is a removable discontinuity. A hole. What is the hole? What's the y value of the hole? The y value of the hole is what happens when you plug it in without the factor. So when we cancel that factor, y is going to be x minus 3 over x minus 2. Give me negative 5 over negative 4. Or 5 first. Or 5 first. There's going to be a hole at x equals negative 2. And y is 5/4. All right. You can find the hole with the graph as well. We didn't talk too much about that. That's how you do it. To find the hole, just look at the function that, what would the function do if there weren't a hole? And then plug in negative 2. And that negative 5 over negative 4 or 5/4. All right, so that's the intercepts, that's the multiplicity. Again, let's use this multiplicity later because we can't include it now because we don't know whether it's going up or whether it's going down. The other things that we were asked to look at were the vertical asymptotes and the y-intercept. The y-intercept is when x equals 0. The y-intercept is going to be, let's look at this form. It's a little easier. When x is 0, we get negative 6 over negative 4. Positive 3/2, or 1.5. Vertical asymptotes, look at the denominator. But notice that negative 2 is not a vertical asymptote. It's a removable discontinuity. So there's only one vertical asymptote here. At x equals positive 2. So we graph that. What about any horizontal asymptotes or slant asymptotes? Also, notice the multiplicity here is 1. So if it goes up on one side, it'll be on the bottom the other. Or if it goes like this, it'll be up on the other side. It means locally it's like 1 over x, or the negative version. Okay. Horizontal asymptotes look at end behavior. And the end behavior looks at the leading terms. X squared over x squared. Okay, so the end behavior is like 1. The horizontal asymptote of y equals 1. So again, we might cross it in the middle, but eventually at the ends, we're going to approach the line y equals 1. All right. And again, you can plug in a couple points to get a better idea of the shape here. But you can also just use Desmos to fill in the blanks. You're going to be looking at, don't do that to me again, Desmos. X squared minus x minus 6 divided by x squared minus 4. Whenever you're checking your answer, always make sure to plug in the original thing. Okay. Well, this looks like, here, let's zoom in. Let's get the same scale that we're using. Negative 10 to 10, negative 10 to 10. So let's check our intercepts, 3/4 and 3. That's good. Removable discontinuity at -2 and about 5/4. Yeah, that's 1 1/4 about. Right here. And that vertical asymptote, we've got that. And the horizontal asymptote is good. So we just connect the dots. The right piece approaches from the bottom. It does not cross actually, but gets very close. And the left piece approaches from the top as a whole, and then keeps going. Another way to think about removable discontinuities is that this function is almost the same as this simpler rational function. Just has that hole. So as soon as we take care of the hole, outside of the hole, these functions are identical. All right, and in this case, right, this horizontal asymptote is indeed never crossed, and we can actually connect it all the way along. 2 more. Let's look at 54. Write an equation with the given characteristics. So we know our equation is just going to be a bunch of factors. Those are the zeros or the removable discontinuities on the top. And a bunch of factors on the bottom as well, which correspond to removable discontinuities or to vertical asymptotes. And then we just kind of fill things in given the information. There's a vertical asymptote at -3 and +6. So -3 is factor of x plus 3. +6, factor of x minus 6. The x-intercepts are at -2 and +1. Intercepts have to do with the top, just like we did in the last problem. Doesn't mention any multiplicities at all. So we'll just not include them right here. Horizontal asymptote at y equals -2. Is that the only thing we haven't used yet? I think so. So we'll use this to find out what A has to be. So the end behavior, we know the end behavior is going to be A times the end behavior, the leading term on the top, leading term on the bottom. Leading term on the top is x squared. Leading term on the bottom is x squared. Okay, so the end behavior is just y equals A. So if we know there's a horizontal asymptote here, and we know this is our end behavior, A has to be -2. You can put the -2 in the numerator if you want, or you can keep it out in front. And every time you're coming up with an equation like this, make sure to check your answer. Okay, let's plot our answer and make sure it satisfies everything it's supposed to. -2 times x plus 2 times x minus 1 divided by x plus 3, x minus 6. All right. What did we all need? Vertical asymptote at -3 and +6. -3 is here. +6 is here. Okay, we got the right asymptotes. We also needed intercepts at -2 and 1. Good, we got the right x-intercepts. And then it also wanted us to have a horizontal asymptote at -2. Is there a horizontal asymptote at -2? Looks like it on that side. Looks like it on that side. We're good to go. Good way of checking your answer right there. The last one I want to look at is 64. Use the graphs to write an equation for this function. Okay. So again, it's going to have the same form. A times, all the factors on the top times all the factors on the bottom. Let's start with the zeros. The zeros have to do with the numerator. Where does this cross the x-axis? Well, it never actually crosses the x-axis, but it does touch the x-axis at x equals 2. So there's going to be a factor of x minus 2. But because it's not crossing, we know the multiplicity of this is even. Maybe it's 2, maybe it's 4. We're not completely certain. But we're going to guess that this multiplicity is 2 right here. It's bouncing off. It's not crossing. And we can also look at the asymptotes. There's an asymptote at -2 and +4. So these are going to be in the denominator. And we're going to know things about their exponents as well. This, oops, did not have clicked. This asymptote has to have an odd multiplicity for that factor, because it goes in opposite directions on either side of this asymptote. So x plus 2 has to be odd. Let's just say it's 1 and see if that's a problem later. Whereas this one over here, the function's going in the same direction on each side of the asymptote. X minus 4 has to be even. We'll say it's 2, and then we might have to adjust later. Okay. The only thing that we don't know, I don't see any removable discontinuities. Look at those steps. The steps 1, 2, 3 in the graphing section for everything you should be checking. And then it looks like there's a horizontal asymptote of 0. It's kind of hard to tell, but it looks like the horizontal asymptote is 0. And the y-intercept, kind of hard to tell the y-intercept too. Maybe it's like a third or a quarter. Is there any nice point that we can use to find A? Is there any point that's kind of obvious here? I don't really know. I don't think so. Some of them are close. Let's just estimate. Estimate that the y-intercept is about a third. I don't see any really nice point for us to use here. Some of them are kind of close, but I don't think there's anything super obvious. We'll estimate y equals 1/3 is our y-intercept. When x is 0, y is a third. Solve this equation for A. This becomes 1/3 is A times 4 over 2 times 16. 4 goes into that. 1/8, multiply both sides by 8. A is roughly a third. So change A to a third. Or you can just have 8/3, or you can have an 8 on the top and 3 on the bottom. And this is our guess. Let's plot it on Desmos, get the same scale, and let's hope it looks similar. So the scale, y is going from -5 to 5. So go over here and say y -5 up to +5. And x is going from -7 to 7. It's a lot easier to compare things if you have the same scale. All right, now let's put our guess. Y equals 8 on the top, x minus 2 squared. And on the bottom, it's 3x plus 2, x minus 4 squared. Does this look... Oh, wait, this looks really good, right? Look how similar these look. That makes me feel pretty confident in our guess. All right. Nice. Cool. All right, that's it. Let me know if you have any questions. A nice long homework problem video for you. I realize it's a little late in the quarter to be mentioning this, but it's a good idea to just do problems by themselves and don't watch this whole thing. You don't want to watch 30 minutes of me talking all in a row. Good luck. Let me know if you have questions.